So I am Rigami S. Casabana from ECE31, and for today's experiment for Power Electronics Laboratory, we will be exploring the instantaneous power, energy, and average power using PSpice. The objectives of our experiment is to simulate power electronic circuit to determine the voltages, currents, and power quantities of our circuit. Second, we aim to utilize the functions to measure the energy and steady-state autonomous current from our circuit. So I hope you are familiarized with the functions of our PSpice, so it will be easier for us to navigate the application. So enjoy and have fun doing your circuits. To set up our experiment number 2, instantaneous power, energy, and average power using PSpice, we have to open our PSpice application from our computer. Now, for our procedure number 1, we have to create a voltage-controlled switch in PSpice by creating a new project. And then, we have to choose or select the analog or mixer Eyyyy and name it as experiment number 1. And we should click OK. Of course, do not forget to select a location for our experiment number 1. For this experiment number 1, I selected the folder for Power Elecs, so my file will be organized. So select OK. And then let's press OK. Now, choose Create a Blank Project. And then click OK. And you will be directed to this part of our software and application. Now, we have to create the circuit as shown in this picture. Now, to create our circuit, we have to click Place, and then PSpice component, and then we have to use vSyn for the source. Since it is not visible here in our options, we have to search for the specific component. And then after clicking the vSyn option for the component, let's to place our part, we have to click it here and then drag our cursor to place the vSyn component. Now press escape. Set. Now we have to set the voltage source amplitude to 10 volts and frequency to 60 Hz and the resistor to 5 ohms. You can set the value of your voltage by clicking on the text and then setting the value here. So our VF will be 0. Set the value of your parameters by clicking on the text and then setting up the value here. And then click OK. Next, we have to set up the value of our voltage source amplitude to 10 volts and then click OK. Now, for our frequency, we have to set up 60 Hz frequency for the voltage source and then click OK. We have to connect our resistor in the circuit. So we just have to type here resistor and then find the appropriate resistor for the circuit. So here it is. And then click here so we can connect the resistor in the circuit. If you want to rotate your component, you just have to type Ctrl R and then place your component here. Of course, you can set the value of the resistor by clicking on this part and then setting up the value to 5 ohms. And then click OK. And now let's place a ground on our circuit. So let's just select this first option and let's put it here on this part of the circuit. And then press escape. Now for the last part of the circuit, we just have to connect all of these components so that we can have a proper connection, and after that we will be setting up our circuit for a transit cycle. So we are already done with setting up the parameters of our circuit and constructing it. Let's zoom it and we will be proceeding with our simulation. So let's click here in a new simulation profile and let's create a new simulation, and then let's rename it experiment part 1. So let's create it, and after that there will be a pop-up here in our desktop which will allow us to set the simulation settings of our ORCAD, and then here we will be selecting time domain transient, and we will be setting the run to time of our simulation. So let us set our run to time to 16.67 milliseconds. So in seconds, it is equal to 0.01667. And the start saving data after is 0 seconds. Click apply and then click OK. Now, let's click this run button here, which is run PSpice. And then as you can see, there will be a pop-up here in our desktop. And here we will be adding the traces of our output waveforms for our experiment. So notably, in the simulation, we will be testing the instantaneous power, the input voltage, as well as the current in our R1. Now, we will be adding the traces. So for our power, we will be adding the trace of the R1, which is W parenthesis R1. This will be the green line here for the green waveform, and we shall add another trace which is for our input voltage. So our input voltage is V, and checking on our circuit, it is from V1. So going back, so it's V and V1 and positive. So we should add the trace. So as you can see in the output waveforms, the green waveform is our instantaneous power, and the red waveform is our input voltage. The red waveform is our input voltage, which is a sine signal. Now, adding the traces of our resistor, measuring the current across it, we will be adding the trace of I, or the current across the resistor 1. So here on the graph, we can see a blue output waveform which signifies or pictures out the output waveform for the current across the resistor. As you can see, the output waveform for the current across the resistor is flowing from the negative phase. Notably, if we want to let our current across R1 flow in its positive cycle, all we have to do is just put a negative sign here, or let's just contradict the operation of our expression. So as you can see, the output of the current across the resistor is now flowing on its positive cycle. As what we can observe from the output waveforms of our instantaneous power, of our input voltage, which is a sine signal, and our current across the resistor, which is the blue output waveform, we can see that as the positive cycle of all of the waveforms are approaching to our zero or to a specific point, they are approaching a possible phase shift. Wherein here in our AC sinusoidal input voltage, wherein it changed from the positive cycle operation to the negative cycle operation, the output waveform of the current across the resistor also had a phase shift from the positive cycle to the negative cycle. Meanwhile, the instantaneous power output waveform remains the same, thus providing us diagram where our traces shows the voltage, current, and corresponding power waveform. As the voltage and current waveforms are both in phase, as you can see in the waveform, during the positive half cycle, when the voltage is positive, so here it is, okay, when the voltage is positive, the current is also positive, as you can see here. So the power is positive as well, which is the green output waveform here. But during the negative half cycle of our voltage source, the voltage is negative. So this means that the current or the blue output waveform here will be negative as well, which will be giving us another positive cycle output waveform for our power, because instantaneous power is the product of our current times our voltage, which will mean that if the voltage and the current is both positive and both negative, then a positive instantaneous power will be delivered by our circuit. Now, we will be adding another trace to our output waveforms, which will be showing us the average value or the output waveform for the average value of the instantaneous power, which is denoted by the symbols. So we will be adding the trace. As you can see here, this output waveform, which is the color violet, denotes the average power of our circuit. The output waveform is notably different from our instantaneous power output waveform because average power is found or derived by multiplying the RMS value of our current and voltage compared to our instantaneous power, which is the amount of power given in a specific amount of time, which can be derived by multiplying the normal values of the current and the voltage. Now, technically speaking, we can obtain values from our output waveforms by clicking in our cursor on. And as you can see here, when we measure the peak value of our instantaneous power here, we can see that from the side, we will be deriving a 9.985 value of power. Notably, when we try measuring the peak value of the other output waveforms, which is our input voltage, it is quite different from our instantaneous power and our average power, but it is noticeable that all of the output waveforms are in phase with each other. Meanwhile, the peak value of our input voltage is 9.9 volts. Notably, from our data here on this part of the screen, it is notable that the peak current or the current across the resistor is almost 1.8206 amperes. So those are the parameters that we can measure from our output waveforms. And lastly, when we want to measure our average power, all we have to do is just click here on the side of our screen, and then let's drag the cursor all the way to the last point of our output waveform, and then let's check the value here. As you can see, the total average power will be 10.070 amperes. Now, validating the PSpice results with our computations, theoretically, computing the value of our current across the resistor give us the formula of voltage over the resistance, which is 10 volts over 5 ohms, giving us a total value of 2 amperes, which here in our PSpice simulation giving us a value of 1.9539 amperes, approaching to approximately 2 amperes we computed. Now, computing for our instantaneous power with the formula current times the voltage, we will be having 2 amperes times 10 volts, which is the input voltage, which will be giving us 20 watts, which here in the PSpice simulation gives us a value of 19.992 watts, which is approximately 20 watts. This proves that our simulation in PSpice is correct, as well as the computation of our theoretical values. So to summarize our part 1, instantaneous power is the total power at the given period of time, while the average power is the power at a given cycle. Now, we will be proceeding with the experiment part 2. The second part of our experiment number 2, which is the RMS section, we are given another circuit which we will be constructing in our PSpice, now with a different input voltage, which will be providing a pulse waveform voltage source, which comprises of a square wave as seen in this figure. Also, instead of a resistor, we will be connecting an inductor to our circuit. This part of the experiment, we are able to construct the RL series circuit, and in this part, we will be editing the simulation settings, wherein we will be editing the run to time of the simulation, wherein we will be basing it on our figure 8 here on the PDF, wherein we will be considering 100 milliseconds as our run to time. So we will just set up here 100 milliseconds is equals to 0.1 seconds, and we should click apply and then OK. So let's just wait for it, and then there will be a pop-up here on our desktop. So let's just maximize it. So for our part 2 of the experiment 2, we are going to test the current in R1 as well as the steady state RMS current. So let's add trace here. So we will be measuring the current at R1, so it's IR1 here. So as you can see, the output waveform is starting from its negative half cycle. So let's change it here. Let's contradict the sign of our output waveform. So it will be starting on its positive cycle already here. And then let's add another trace, which is the RMS value of our current, type RMS, and then close bracket, and then let's type here the current across the R1. So let's type RMS, and then let's enclose it with our parenthesis. Then let's consider the current across R1, then let's enclose it to another parenthesis, and then let's click OK. So as you can see, this blue output waveform here is the output waveform for our RMS current across the resistor. Notably, we measured or we plot the trace of the output waveform for our current across the resistor instead of the inductor, because notably, since the inductor and the resistor is in series, the current waveform for both of the components will be the same. We can test it here by adding the trace of our current across the inductor. So let's add the trace of our inductor. So as you can see, the blue output waveform here is the output waveform for the current across our inductor, which is just the same with the output waveform of the current across our resistor. This explains the series connection of the resistor and the inductor, which proves that when two components are in series connection, the current flowing across both of them will be the same. Also, we can see here that the current rises to its peak value here and then decreases exponentially with this output waveform. Also, the RMS current decreases exponentially because in an RL circuit or a circuit with a resistor and an inductor, the voltage decreases in accordance with our time, meaning as the time passes, the voltage across our RL circuit decreases while the RMS current increases exponentially to its maximum peak value, and then just maintain. Our RL circuit composes of two components, inductor and resistor, which proves that the voltage equates to I times R. And notably, since the inductor and the resistor is connected in series, this proves that our current output waveforms for both the inductor and our resistor will be the same as well. So, now for our last touch, let's turn on our cursor and then let's measure our RMS current up until the end. So as you can see here on our table, our RMS current equates to 4.6614 amperes. As a conclusion, using the PSpice type software, we are able to measure the value and understand the instantaneous and average power of a resistive circuit as well as their output waveforms. Technically speaking, it was proven that the instantaneous power is the power of the circuit at a given instant of time, while the average power is the total average value over a cycle of a number of cycles. Moreover, in a series RL circuit, it was proven that the current flowing through the resistor is the same as the current flowing through the inductor, thus resulting to the same output waveforms. Lastly, the value of current in an RL circuit begins at 0 and increases to its peak limit value at a given time constant before decaying exponentially. So that's our experiment number 2. I hope you learned something and enjoy while watching my vlog, and I hope we'll be seeing on our next experiment. Thank you and may God bless us all.